very good day to doctor. My name is Lab5, AE1900077. I'm from Group 1, Session 3, BEV20501. Today I'm going to do a presentation on exercise 5, measurement using DC bridges. So in our lab sheet, we have two kind of resistance measurement with DC bridges, which is a whetstone bridge and a Kelvin double bridge. So for a whetstone bridge, it is ideal for a measurement resistance of a medium range, which is as low as a milliohms, and it is also a DC resistant bridge. So for the next Kelvin double bridge, it is going to use in a low resistance measurement, usually less than 1/10 of a resistance ohms, and both are going to use in the determine the unknown resistance in the bridge. So for the activity 5.1, in my case that I'm going to present is I'm using a Proteus software with a parameter of a whetstone bridge given over here. It's based on the table 5.1. So I'm going to construct components with a battery with a DC voltage, and I'm going to have a resistor of a 0.6 volt metal first, and I'm going to have a potentiometer or variable resistor as well, and I'm going to construct it using this. We have 3 fixed resistor and 1 potentiometer, and I would connect with a emitter as well, DC emitter, to show the value, and ground. Forget about ground. Okay. Over here, and it's going to plug over here. This one is going to touch here, and I'm going to connect our battery. Okay. So I'm going to touch it. Okay. This size here. So I'm going to have our case that 10 volts of DC supply, and R1 of 10k ohms, and R2 will be 2.2 kilo ohms, and R3 is Rx unknown will be 5.6k, and rename it to X. And this one I can change to microampere, and we have a maximum value of 30k, so I'm using it. So according to the given, I'm going to show it until 0 to adjust the arm resistance to 0 microampere. So I'm going to adjust it here. The nearest to the 0 ampere will be positive 0.541. So it's out of it's almost 85% of 30k ohms, so almost 25.5 kilo ohms, and material reading is over there. So I'm going to justify my answer using this formula given. Rx unknown equals R2 over R1 times R3, so I'll get 5.61 kilo ohms of Rx. So it's nearest to the 5.6 kilo ohms over here. So I'm going to do the next sample given, which is I'm using the 1.5 kilo ohms on a Rx unknown resistor. So I'm going to change this one to 1.5 kilo ohms, and I'm going to test it with this one. So I'm going to switch it to the nearest 0 ohms. It's positive 5.79, microampere, so it's equivalent to 23% of 30 kilo ohms, which is 6.9 kilo ohms here. So I'm going to put it in my sample 2, and it's equivalent to 1.518 kilo ohms. Okay, so basically it's just to determine the unknown resistance of the resistor over here. That's it for my presentation. Thank you.
Hello, Assalamualaikum. My name is Elisa Afira binti Hazaa and my chemistry number is AE1900067. So for the condition, unknown resistor S is equal to 0.01. The millivolt is not at 0, so we need to change the RBs. So the first RB I set to 994 and the other RB is 1012. So as we can see, the millivolt is equal to 0 millivolt. So we change to open and change the S to 0.06, open, and the millivolt is now not in zeros. So we need to change the RB again to 990 and RB is 999.9. Oh, sorry, close. So, yep. And the resistor value is 0.006. That's all from me. Thank you.
So a very good morning to all the lecturers who is watching this video presentation. Today my name is Lei Jinzo. I'm from Group 1 Section 3 and now I'm going to explain with you about the Lab 5 activities 3 in the report. So the first question is explain all the result in activity 1 and activity 2 respectively. So based on the result in activity 1, the arm resistance R3 was adjusted by 85% to get a balanced condition of ammeter reading with 0.41 microampere, and then the formula of R2 over R1 multiply with R3 was used to identify the value of unknown resistance and Rx. The calculated value is the same way as the Rx that stated in table 1, which is my friend has been stated before, just before this. And next, based on the result in activities 2, the Kelvin double bridge stimulator was used to determine the unknown resistor. So in condition switch to closed mode, the RA and RA was set up to 1000 ohm, whereas RB and RB was set up to 994 ohm and 1012 ohm respectively. And for low resistance is 0.0098 ohm, and then we get the unknown resistance Rx is also 0.0098 ohm. Beside that, in the condition switch K to closed mode, the RA and RA was set up to 1000 ohm, whereas RB and RB was set up to 990 ohm and also 999.9 ohm respectively. So the low resistance is 0.06 ohm. Then we get the unknown resistance Rx is 0.006 ohm. So for the question to discuss the simulated and calculated value of resistors used with balanced Wheatstone bridge and also Kelvin double bridge respectively. So first, for balanced Wheatstone bridge, the simulated result that we get was the same as the calculated result of unknown resistor, because the same value of R1 and R2 which has given, and also the adjustment of R3. So next, for the Kelvin double bridge, the simulated result that we get was also the same as the calculated value, because directly adjust the value in the white boxes of respective elements to get a zero deflection on the millivolt meter pointer. So question 3 is justify the percent error for the resistance measurement using balanced Wheatstone bridge and Kelvin double bridge respectively. So the Wheatstone's brick is capable of providing up to 0.1% accuracy. The accuracy may be comparable to 3% to 5% error typically found in resistance value measured with analog ohmmeter. However, the unknown resistor value can be obtained from two arms of the Kelvin double bridge, typically with its measured 1 to 0.00001 ohm with an accuracy plus minus 0.05% to plus minus 0.2%. So, question 4. Differentiate between the accuracy of Wheatstone bridge and Kelvin double bridge for the respective resistance measurement. So, the differentiation is very obvious. The accuracy of 0.1 for a Wheatstone bridge is quite common with a Wheatstone bridge exposed to the accuracies of 3 to 5% with the ordinary ohmmeter for measurement of medium resistance. But for the Kelvin double bridge, the unknown resistor value can be obtained from the two arms of Kelvin double bridge. Typically, it's measured 1 to 0.00001 ohm with an accuracy plus minus 0.5% up to plus minus 0.2%. So, the question 5 signify the bridge to use for measure of test resistor having a value around 50k kilo ohm, which is from our group answer is the Wheatstone's bridge is more suitable. And question 6 is in contrast, the unbalanced Wheatstone's bridge is often used for measurement of different physical quantities. So first, determine the condition of our unbalanced Wheatstone bridge. Once the value of resistor are fixed, the value of unknown resistor has to be found out by using the Kirchhoff voltage and current law. It means that the output voltage in the circuit is not equal to 0. Next is state and briefly explain what are the physical quantity that can be measured by using an unbalanced Wheatstone bridge. So it should be a temperature and also the strain. That is all from my part. Thank you.
So in conclusion, based on all the activities in experiment 5, students get a better knowledge in understanding about two methods in order to measure resistance, which by using Kelvin double bridge and Wheatstone bridge. The calculation to find the unknown impedance are successfully done by using appropriate simulation tools such as Proteus for Wheatstone bridge and Kelvin double bridge simulator. Besides, by repeating these two experiments using our own values, we can understand well as well as to see how the operation of each resistor in these two bridge works.